So welcome to the 519 Colloquium, and as it turns out, also welcome to 590G, which is one in the same today. So in 590G this quarter, we're looking at applications or domains, application domains that could be good candidates for what I'll call domain-specific processors. So these are processors that sit somewhere between the general purpose microprocessors that are on our desktops and ASICs. So we've been investigating various applications or domains of applications that might be good candidates for special hardware assists on these processors, and software radios is one such candidate. So I am pleased to introduce you today to Vanu Bose, whose life at the moment is software radios. He graduated from MIT in '99, and his thesis was software radios. And now he has started a company called Vanu.com, and their product is...
Not .com.
Vanu Inc., maybe?
Yes.
Vanu Inc., whose product is software radios, and it is a product. They are, in fact, profitable. This is year 2.
3.
Year 3, and they're profitable.
Yeah.
So with that intro, I'm turn it over to Vanu.
Thank you. So what I'm going to talk about today is the research challenges in software radio. As you'll see, software radio is it's a ridiculously cross-disciplinary pursuit involving everything from like digital communications, DSP, distributed systems, languages, algorithms, etc. But some of the really interesting problems lie in the boundaries between these different areas. So this is more of a research survey talk. I'm going to tell you about what a software radio is, and then highlight some of the areas where there's interesting hard problems, some we're working on, and some that we hope other people will work on. So let's start with what is a software radio? What is a Microsoft frozen computer? There we go. Okay. So what we have today are hardware radios. What I mean by that is a radio is anything that uses wireless for communication. So that could be one of these things. It could be a television, could be a wireless LAN, your garage door opener, a walkie-talkie. They're all things that use wireless for communication. And these are hardware radios because in this there's a chip, which in this case makes it a CDMA cell phone. The chip's made by Qualcomm. And all it does is CDMA communications. There's nothing I can do to turn this into my 802.11 LAN or to open my garage door when I go home or make it my cordless phone at home, even though that'd be great if I could have one device to do all those things. So what a software radio does is says, let's take all the functionality that makes this cell phone different from a LAN, different from your walkie-talkie, and move all that processing up into software. So from a communications point of view, what that means is moving all the processing from layers 1, 2, and 3 up into software. So we're now doing layer 1 in software. Now we can make one generally reprogrammable device that we can change the software on and turn it into any of those devices. So it sounds simple, but there's a few challenges along the way. So let me answer the question, why the heck you would want to do this before we get into how you would do this. Well, one thing is, it certainly enables multifunction devices. So in the cellular case, it'd be really nice if I could go anywhere in the world and turn on my phone and download software from the local network and communicate with what's ever there, whether it's in Europe or Asia or here, or when they upgrade standards, if I didn't have to get a new phone, it would just download it. Or if I went home and it would be my cordless phone and I wouldn't have to pay cellular charges. That would be nice. In the infrastructure, these are the wireless base stations that are around that your phones and networks talk to. They have a serious problem. They're very expensive pieces of equipment. They're hardware radios. They do one standard. Now, you're probably all familiar with Moore's Law, factor of 2 every 18 months. Digital communication, there's been rapid advances. Well, look at cellular standards. We get one every 10 years. There was AMPS that was deployed in the 80s. The digital stuff, TDMA or GSM, was deployed in the 90s. And maybe sometime this decade we'll get 3G. Now, the reason for this isn't that technology is moving so slowly. The reason is that it's really expensive to build out all this hardware and base stations all across the country. To give you an example, the estimate of the cost for AT&T to upgrade their entire network to 3G is $10 billion. Now, you roll out $10 billion, you can't afford to roll that out again in 2 or 3 years. So they need 10 years just to get a return on investment there. Now, if that infrastructure you rolled out was software upgradable, Well, software downloads are a lot cheaper than rolling new hardware, so you could get upgrades and more technology out to the public faster. So that's one big motivation. The software upgrades make it faster and cheaper to get new standards and new services. For example, now there's data services, email, SMS, whatever it is. Those should just be software upgrades, just like on the web when you get a new service, you don't have to install a new piece of hardware. You download a new protocol or plugin. There's another advantage which I honestly didn't realize at first until we started talking to customers. But there's a tremendous risk. All these wireless companies like AT&T and Singular are out there trying to decide, well, what standard are we going to go to next? There's like 5 different choices. There's GPRS, there's 1xRTT, there's WCDMA, there's there's CDMA 2000. And there's tremendous risk in this. This is the $10 billion bet they're making on rolling out that equipment. And if they're wrong or the other one becomes more popular, they're basically done. So they really like this from the point of view that, hey, I can roll this out and maybe for just an extra $1 billion, I can software upgrade and change the system if I made the wrong bet. So that's another advantage of the software flexibility. And finally, there's new sources of revenue. This is what wireless people really care about. The only thing they really care about, actually, that they'll add to their network is something they can charge you an extra $5 or $10 a month for. So if it's data, if they can charge you $5 a month, they want that. If it's email or paging or whatever. But today, to roll out any new service requires a change to the standard, new hardware on the phones, new hardware on the base stations. They happen slowly. Again, if those were software upgrades, you could get those out more quickly, and you could do more service experimentation. Right now, people have to kind of guess that, yeah, there's going to be people willing to pay a lot of money for this and roll it out. And people haven't been paying a lot of money for wireless data on their cell phones. But if it's cheaper and faster to roll out, we'll experiment faster and hopefully figure out what is really useful more quickly. So that's by way of background and motivation on software radio. So here's what I'm going to talk about today. First is, what is it? Not from the 10,000-foot level, but what's the system architecture of a software radio? And as a side effect, looking at embedded software engineering and why it's so pathetic compared to the kind of software engineering you do in workstations, networks, or PCs. Algorithms. This is, I think, the most interesting and potentially fruitful area of research that's come out of software radio, which is take traditional digital signal processing functions, fast Fourier transforms, Viterbi decoders, et cetera. And I'll talk about what implicit assumptions people make when they design them and how the kind of algorithms approach you learn in a computer science department can be applied to these problems and get much, much better results. I'm going to talk a little about language design and why we might need a radio description language. Then talk a little about what it would take to build software radio in the infrastructure, in particular large systems that have to be scalable to hundreds of channels, and they have to be sold to telecom people who won't buy anything that isn't 5 nines reliable. And finally, I guess the 590G part of it is a few thoughts on processor design and what would you want to do if you were to build a domain-specific processor for software radio. So let's start with software radio and defining a few terms. So one important thing to note is that just because you have software in your radio doesn't make it a software radio. In fact, now that it's become a popular term, there's lots of people who come around, oh, we've been building software radio for 10 years. Now, if you have a single function radio and you chose to implement some of the functions on a DSP and then you closed the box and shipped it and you could never change it, I don't really care whether you chose software or hardware to implement it. You don't get any advantage from it except maybe in your manufacturing or design costs. So that's a traditional radio implementation in software. Now there's a class of systems that have become known as software-defined radios, SDR. In these systems, software has control and configuration of the radio. So a simple example of a SDR is a dual-mode cell phone. So in a dual-mode cell phone, the way most of them are built today is they build in 2 ASICs. For example, one for CDMA and one for analog. Now software, there's a little software running a microcontroller which is smart and wakes up and looks and sees what system coverage area you're in and decides to run the appropriate ASIC. So the software has control over whether it's going to be an analog phone or a digital phone. However, the software can't do anything if you're in Europe and the only thing there is GSM and you didn't have that built into the phone to begin with. So SDR gives you configurability and control over a number of built-in modes to begin with. Of course, what you'd really like is to be able to just add new modes. And that's what a software radio is. So it does everything that a software-defined radio does in terms of control and configuration. But it also says we're going to implement all the software processing, all the processing in software, or when I say software, implement all the processing in some way that is totally flexible and reconfigurable. Now, when I go to a new country or buy a new system, I can download software and communicate with it directly. So software radio is the most flexible system you can build. It does have limitations. Doing everything in software takes a lot more processing power. So you will, if you just want a single wireless standard, you'd always just build an ASIC. It's going to be cheaper in volume and it's going to be lower power. If you want flexibility of more, then you've got to give up some on those costs. So this is a very messy architecture diagram, which I just wanted to throw up all the different components and tell you what's in there and how certain things interrelate. So let's start at the bottom. There's some hardware. All those blocks and all is just a graphical way of saying, here's what I need the hardware to do. It's got to go out and grab some piece of the RF spectrum. In fact, the system we have running in our labs can go grab a chunk of spectrum anywhere between 2 megahertz and 2.5 gigahertz. So if I'm doing a LAN, I'll grab 2.5 gigahertz. If I'm doing an analog cell phone, I'll grab 800 megahertz. Has to convert that down to some frequency where I can digitize it, and digitize it and stream it into some memory where I can access it. Now, the important thing is that process hasn't done anything except give me a digital copy of that spectrum in memory. I did no pre-filtering, no equalization, et cetera, in the hardware. Because if I had, well, while that might be useful for the standard I'm using now, it's not going to be useful for other standards, and I've limited my flexibility. So the hardware, the job of the hardware is to get a digital representation of as big a chunk of spectrum as possible into memory. And then the software has to start working on it. So the software, the job of the software is, in a typical situation, first select out the channel or channels that I'm interested in, do all the equalization, demodulation, all the way to layer 1, the layer 2, the layer 3 processing. So how do you do that? Well, remember, we don't want just one system. We want to be able to reconfigure this radio to do many, many different things. So I need some software that has different standards. And I need to be able to run those different standards. Furthermore, I want that software to be portable. Because in the future, you know, if we all get in this room and we want to communicate, I can give you, or through some bootstrapping process, download you a piece of software which maybe is a great networking standard for ad hoc networking in this auditorium, and then we can all run it. But I don't want to know what processor and OS you're running necessarily, or at least the processor. And I want that to be completely portable. I also want it to port to new generations of processors that are faster or lower power. If I have to rewrite all the software for every generation of processor, it'll be too expensive. We'll never be able to make a business out of it. So that's where the radio description language comes in that I'll talk about. And the signal processing is basically done by two components. The libraries, which are very simple, just functional units, filters, decoders, et cetera, which are then combined with this middleware called Sprocket. The middleware is there to handle timing constraints and I/O between the modules and with the system. So what happens is you get an RDL waveform. The interpreter looks at it. RDL is basically a complete set of instructions for how to build a radio. It pulls apart the appropriate libraries that's needed according to the instructions, connects them in the right way, and starts a radio running. And that's what gives you your entire system. Now, you can change it at any time by executing another RDL waveform and changing the radio that you're running. So how does this sort of system architecture compare to other things? Well, Joe Mottola is he works at MITRE Research and has done probably a decade's worth of writing and research on software radio. And he wanted to compare different software radio efforts. So he came up with a phase space that had two primary axes. He said there's two things that we really care about in software radio. One is flexibility. So that's the horizontal axis here. And he put down some qualitative measures of flexibility. ASICs on the left being the least flexible, because you've got to spin a whole nother chip to get another function. And general purpose processors being the most reprogrammable on the right. The vertical axis is what he called digital access bandwidth. How wide of a band of spectrum is accessible to that flexible processing? That's important because for one of two reasons. Wider bands either allow you to do higher data rates or support more individual users on individual channels. So he mapped a number of different technologies. Like the C up there was actually a Lucent reprogrammable cell site that they were building, which actually used ASICs and FPGAs to give you some functionality. D was the first software radio project ever called Speakeasy, which I'll talk about on a couple slides. And that used a combination of DSPs and FPGAs and did some IF rate processing. The ideal software radio would be sort of all the way up to the right, out at infinity. You know, when we can digitize DC to light and process it on our microwatt Pentium, we'll be all set. But we're not quite there. And then the V was our technology back at what we did at MIT. And you know, the reason I like this slide is that we're the closest to the X. But the really important thing is, how did we get there? So in our research at MIT, what we said was, the most important thing that software radio brings to the table is flexibility. So let's maximize this axis out first. So we did that, but processors were pretty slow back then. And we were about here. And we couldn't even run an analog cell phone in real time. And people laughed at us. You know, they said, well, why would you want to do this in software? You can't even do the most basic analog systems. We already have digital systems. But we carefully designed the systems so that the bottleneck wasn't in the A to D converter, wasn't in the I/O, wasn't in the OS, but was actually in the processing. So every generation of Moore's Law, we were able to do twice as much. And the processor, which couldn't run one analog cell phone in real time today, can handle 10 cell phones simultaneously on a single processor today. And we got there by just writing Moore's Law. By the way, this is a great strategy for doing a thesis. You build a system, then you take a couple of years off, and then you get up there, and then you're done. So that's and the other thing is, we can continue getting closer to the X by writing Moore's Law. Now, there's one other axis which you could throw on here, which makes things a little more difficult. Say we had a third axis, which is power dissipation. Clearly, ASICs are going to be the best, and general purpose processors being the most flexible and reprogrammable are going to be the worst. Fortunately, there's a lot of effort now in low power processors driven by PDAs and cell phones, things like the X-Scale from Intel and various other efforts, that while they're not at cell phone battery life yet, what we've seen on people's roadmaps says that in 3 years, they will be to where cell phones are today. And then once you can meet the battery life constraint with software and provide the user with many, many more standards, there'd just be no reason to do it any other way. So let's talk about the traditional approach to building DSP systems and software radios in particular. Now, people write, you know, if you open up any DSP system that has a processor in there, it's got a DSP from Texas Instruments or Analog Devices, and all the software is written in assembly code. Why do they do this? Well, let me tell you, let me back up. Let me tell you why this is bad first. So the big thing is, you know, assembly code is not portable. And in particular, assembly code for DSP is really not portable, because there are really weird architectures with all kinds of, they let you really get at the guts of the processor to try to eke out every little bit of processing. You're allowed to play in the delay slots of the pipeline. You have special purpose registers that only can call certain operands in certain kinds of situations, which are really good for some common DSP functions, but really bad if you're trying to write a compiler to use these things. But the reason people do it is, until recently, you needed to eke out every single MIP from this thing that you could to get anything useful. So there's two good examples of software radio systems built this way. The first was Speakeasy, which was the first software radio project done by the US military in 1991. The military has a terrible radio interoperability problem, because somebody decided to give every branch of every service a different radio, and they go on joint operations and they can't talk. And there's been fatalities in the Gulf War and Grenada directly linked to this. In fact, I have some time for some digression. There was a really classic example from Grenada, which was told to me by a general, but he wouldn't repeat it publicly, that you remember this sort of silly invasion of Grenada they had, where the Marines landed on the beach, and the Army landed on the other side of the island, and they sort of fought their way to the middle. And it was night by the time they got to the middle. And the Marines saw some people moving up in the hills. They couldn't raise them on the radio because the Army had a different radio, so they assumed they were hostile and fired on them. Fortunately, there was some enterprising Marine who knew that, wait a minute, the Army's out there somewhere, and we haven't seen any other resistance, so something's going on. The situation got resolved by that Marine walking up to a payphone in Grenada, calling the Pentagon, and getting orders sent out to both sides to straighten the situation out. I've heard that within 48 hours they decided to start the Speakeasy program. So the first prototype was actually begun in 1991. And at the time they chose the Texas Instruments C40 DSP running at 40 megahertz. It was the fastest thing available. It was the right choice. But 40 megahertz wasn't even close to being able to do what they needed to do. So they first built quad packs of C40s, boards with 4 C40s on them, which of course didn't have like SMP support, so they had to build all this extra circuitry. And then they put multiple quad packs together and built the system. So in about 95, I was about just 6 months into my thesis at this point, they came out with the first system. This was the first software radio system ever. It involved about 200 processors and fit on the back of a truck. But it worked, okay? I'll give them that. But I looked at it kind of naively and said, well, why are they using those 40 megahertz C40s? TI and Analog Devices has 166 megahertz processors out now. And the answer was the software. It was tied not only to the C40, but their specialized quad pack architecture of the C40. So they had spent 3 years writing software for these 10 different waveforms that was obsolete before it ever came to market because Moore's Law had far surpassed them by that time. They would have been better, writing C code and sitting back for a couple of years. There's also a recent commercial example. A company called AirNet has built a AMPS and GSM reprogrammable base station using the TI C54X series DSPs. And to do more advanced standards, they needed more processing. They're trying to go to the C6X series. I've heard from their engineers that basically nothing's porting and they're having to rewrite everything. Their costs are overrunning. They just downsized from 350 people to 120 people. And the portability might kill the company. So these examples led me to realize that software portability is our #1 goal. Because if Moore's Law stopped, I might have a different story. But as long as we're going to get faster processors or be able to make SMP systems that can give us more power, or more low-power processors keep coming out, we need to port the software because the majority of the effort and money in building a system now is in the software, because that's where we're doing all of layer 1, 2, and 3. So there's some motherhood about assembly language that you probably know, is that it's really poor on programmer productivity. This is why people invented high-level languages. Too many lines of code, the development tools are horrible. Try giving your code to someone else to read and debug, there's just no chance. But again, the reason people do it is that you can eke out lots of performance if you spend hundreds of man years on a process. In fact, Intel has a lab in Russia with all these ex-Russian defense research people, and their entire job is taking functions and libraries and hand optimizing them for Intel processors. They don't have to pay them much, but that only scales so far. So, the desktop world, the systems world, whatever you want to call it, the CS world, went to high-level languages in the 60s. The DSP world hasn't gone there yet. Now, I'll give them one thing and say they couldn't go there because of the performance issue. But for a lot of things you can now. There's pretty fast, not only DSPs, but very fast general-purpose processors that, in some cases, outperform DSPs on DSP functions. Not only do you improve program productivity, but software reliability improves as you get better debuggers and better test harnesses and better development environments. This is extremely important because for software radio, we have to go in and get FCC approval. And the FCC has to have a pretty high degree of certainty that there isn't a software bug which is going to take this thing and cause me to radiate something in the FAA aircraft communication bands, which stops all aircraft communication. So program verification is important. Testing and debugging strategies are very, very important. So this is my first plug for something that I would like to see done that we're not doing in terms of high-level languages. There's no good support in high-level languages to reason about timing. And this is a very, very important thing when you're doing real-time digital signal processing. There are end-to-end latency constraints, and there are, for example, in the GSM system, when you receive a signal from the base station, you'll get assigned a time slot to transmit back on. And maybe your time slot 5. Well, time slot 0 is known to start X number of milliseconds after you receive the signal from the base station, and each time slot is so long, so you can calculate at what time you need to transmit that out. But there's nowhere in my C program to say, this has to be transmitted at time t, or within a window before this or after this time. We solve this problem at the system level by building a middleware which handles I/O and timing by timestamping all data as it enters and leaves the system. And you're actually running in sort of a virtual time environment where you have buffers and you keep track of timestamps. And on the input or output, the timestamps get reconciled with what the real-time clock says. But what we really need is higher level support to reason about and provide guarantees, or at least ways of checking timing constraints on systems at a high level language. And the other thing that we've done a lot of work on is looking at new algorithms for what are, in some cases, very, very old DSP functions. It turns out there's a lot of things you can do by freeing yourselves from the algorithm design constraints of hardware and looking at what software has to offer. That's what I'm going to talk about next. So in many DSP algorithms, things like convolution, FIR filter, Viterbi decoders, fast Fourier transforms, there are many assumptions which are made which I actually think are kind of implicit. People don't, it's just so ingrained in the way you design things that I'm not sure people realize they're making all of them. One is certainly that you design an algorithm to minimize the number of multiply accumulates. The FFT is a really good example of this. The Cooley-Tuckey algorithm, which I'll talk about in the next slide, minimizes multiply accumulates. However, if you look at what's available in the processor world today, on a PowerPC, you can actually do a MAC, and it has a single cycle MAC in it. But a cache miss can be 250 cycles. So I could design an algorithm with two orders of magnitude more MACs if it saved me a cache miss, and I'd be ahead. Whereas the traditional DSP design of minimizing MACs doesn't make sense. If I showed that algorithm to a DSP guy, he'd say, this is a horrible algorithm, has too many MACs, I can do better. But that's no longer the relevant cost. Another sort of, but the second point here, by the way, is starting to change. I would say, well, when I was doing my thesis, there was this mantra among DSP people that data caching was just really bad. And that's why you couldn't ever use a general purpose processor to do DSP. The canonical example they use there is the fast Fourier transform, which it turns out there's many cases where you want to do FFTs on data sizes that are much larger than any cache you'll have. And the way the algorithm works, there's this thing called the butterfly computation, where you sort of take something from this end of the array, combine it with something there, take something there, combine it with something there, and you're just constantly thrashing your cache. And they'll point at that and see this is why you don't want a cache in a DSP. These types of algorithms are very bad. But if you could keep the data you're operating on in cache, you could really do much, much better. And on the next slide, I'll talk about an algorithm that does exactly that. The third assumption that's often made is that you need a constant amount of computation per output that you get from the algorithm. This is actually a pretty good thing to do in hardware. You have a certain number of transistors there, and that's what you can run every time. And if you can fix it so that it's a constant amount of computation for every output, now you have a very, very good idea of how much time that is going to take, and you can add up the time for each of your modules and figure out what your real-time constraint is. But what happens is, in order to guarantee that this will operate in n cycles, what you end up doing is optimizing the worst-case performance of this module. So a lot of processing can be data-dependent on how much processing is needed. And you end up implementing the processing that's needed for the worst case, and doing that all the time. Now, this, I think, is the biggest difference between DSP-type algorithms and CS-type algorithms. CS-type algorithms are very focused on optimizing the common case. And you'll get some outliers, but hey, in the average, you're doing a lot better. Because of the real-time constraint, DSP algorithms are typically optimizing the worst case, and they're bringing the common case up close to the worst case, which has a lot of implications. The most significant is in low-power systems. Today, you have processors like the StrongArm where you can vary the clock speed. So just imagine I got my cell phone, and I'm outside, and the signal's really strong. Well, I don't have to do all that equalization and filtering that I would do if I were driving at 70 miles an hour through a tunnel. So I could change my processing algorithm, use less power, turn the clock speed down, and save my battery. Then when I get in a bad signal-to-noise situation, I can use more processing and use more battery. So this is a direct by changing the way I write algorithms, I can directly affect the battery life and the experience of the consumer. So I want to give you one slightly more detailed example about an algorithm. And I won't give you the details here, but I'll point you at a place where you can get them. So let's look at the FFT. The traditional algorithm is the Cooley-Tuckey algorithm. And it minimizes the number of multiply adds, and as I mentioned, has horrible cache performance. What happens with an FFT is you can subdivide an FFT into smaller FFTs of size 2 to the n. And in fact, you can keep doing this until you get size 2 to the 0 and you get one element. And then combining them back up turns out to be fairly trivial. Well, this work was done by one of the people was Matteo Frigo, who's actually a researcher at our company now, but this work was done when he was at MIT on an algorithm called FFTW. And he made the observation that, basically what I was saying before, that multiply adds aren't the thing you're really trying to minimize. So he said, well, let me divide this FFT into smaller sizes of 2 to the n until 2 to the n fits in my cache. Then let me stop and run the actual FFT algorithm. Everything's in cache, and it's trivial to combine the results back up. And he got, depending on the FFT size and processor, 1 to 2 orders of magnitude better performance over the traditional Cooley-Tuckey algorithm. So there's a lot of details and graphs and performance numbers at fftw.org, which is a site he maintains. And if you're interested, I think this is probably the best example of how you can look at an algorithm, understanding the real cost, the new cost that you have in software, and do a much, much better job than you can with the traditional approach. All right, so just flipping through the outline here, I want to change gears and spend a couple slides talking about the radio description language. I don't believe it's up now, but next week there'll be a paper on our website which is being presented at a conference talking about experiences of implementing GSM using RDL, which for anyone involved in languages will be interested. And then a few slides talking about infrastructure applications. So going back to our architecture and subtracting a lot of stuff, let's focus on RDL. I want a portable description of a waveform that I can give to anybody in the future with any kind of reconfigurable radio, and they can run it and therefore be compatible with what I'm running. Now, this model is much more like it's not like real-time DSP code. It's more a model like Java, where you have portable interpreted code. And in fact, RDL, even though it's called Radio Design Language, that's actually legacy from when we started designing a language. And it's now implemented as a set of APIs in Java. There's two very practical reasons for this. One is you can get JVMs that run on a heck of a lot of platforms. And two, programmers out in the real world, they just don't want to learn another language. So if you can do it within an existing language, you'll get much more traction. And we are, since we made that switch. I won't tell you what language it was originally implemented in. But so what you really want is you don't want that code can't contain the actual signal processing code because that's going to be specific on the platform. In fact, it might not actually be running software at all. You could imagine a system that had reconfigurable hardware and a whole bunch of different filter modules and decoders, et cetera. This same language ought to be able to reconfigure that system the same way it can reconfigure software. So what you really want to do is settle on a definition of what are the different modules that I can manipulate, what are the parameters I can set on them, and how can I connect them? So if you have a description of the function that this module does, a list of the parameters and how they can be tweaked, and a list of the types of input and output ports that you have on this module, that should, and so far has proved to be sufficient for describing a component of a radio. So a little snippet of some code just to give you an idea of what it looks like. There's actually 5 portions to an RDL program, and there are 3 on this snippet. The first is it's got all the different modules that you need. It's got to declare them, and you'll check and make sure they're in your library. Then you've got to be able to connect them all. So which modules are connected to what and how their ports are initialized and linked. So it's very simple. It's like any directed graph kind of language to this point. Then there's 2 other parts, which aren't shown here because it would be too long. The next part has to configure each module by setting the parameters on that module to whatever's needed for that particular radio. And the last part is the most important. In any communication systems, there are control state machines at a high level that run it. So, for example, in TCP, there's basically a state machine that looks at the acts coming in and makes decisions on what to send back out. In the wireless systems, like when you turn on your phone and make a call, when you send that call request message, there's a state machine that causes a whole lot of different things to happen, a voice channel to get allocated, a back-end call to be mated, some more messages passed back and forth, et cetera. And it turns out, well, state machines are state machines. They're not intellectually challenging. They're very large and complex. And I don't know, occasionally you hear about bugs where cell phones are recalled. It's always because of a bug in the state machine implementation. And one of the reasons is that implementing state machines in assembly language on a DSP is really time-consuming and really, really hard to debug. So what we've done with RDL is we've included a complete description of all the required state machines in RDL. They can just be written in Java. Now, those can either be run directly on your platform as Java, if you can afford the processing, or translated on the platform by the RDL interpreter to whatever's needed. So that is all the information that you need to sufficiently describe and run a radio system. This is an ongoing, as I said, area of research. We're publishing the first paper on this next week. Excuse me, next week. And question? Well, there's a lot more work to be done.
Is this the level on which you anticipate putting in your timing constraints?
Yes, good question. Thank you. In fact, we've started to do that. You need to annotate this with timing constraints about what is the end-to-end latency, how fast do certain things have to respond, et cetera. And we're looking at semantics for that now.
Which part and sort of how do you do that?
In the part that's not shown, unfortunately. Well, actually, no. I think my guess is that it'll end up as a separate section, which is timing constraints between the modules, like there's interconnection constraints, and there'll be a separate section where we have to define those. The way we've chosen to do this is not try to sit down, we did try to sit down and figure out in advance the global scope of all the things we needed for timing. And you just can't figure it all out. So we're just going ahead and implementing radios and figuring out what pieces we need. After we've implemented a few, we'll sit back and see what the right set of constraints is.
How's the scheduling of the blocks done?
So that's not done in RDL. We leave that up to the platform. So in the RDL interpreter, it will know whether you have multiple instruction units, et cetera. And in fact, the key thing, RDL was designed to be the same code can run on our multi-processor base station system as well as a single processor system. So the parallelism is up to how the libraries and interpreter are implemented on the platform, not to the description. We didn't want to get into that level because that reduces the portability. So that's a good segue to the wireless infrastructure. So the infrastructure has some constraints that are very different from these kinds of devices. First of all, it's got to be scalable. For us, we need to put eventually hundreds of machines together to handle hundreds of calls or thousands of different messages, et cetera, as 3G systems handle wider data rates and more users. Availability is huge. I mean, I went down right when I was finishing my thesis and talked to Bell South and said, hey, wouldn't you guys like this cool one base station that could be reprogrammed to do anything? And now, I was talking to the biggest software radio proponent at Bell South, but this tells you the mentality. He listened to me and said, well, we consider putting software radio in the handsets, but we'll never put it in our infrastructure. And I said, why? And he points at his desktop, which is like running 98 or something, and he says, this crashes all the time. We can't have our infrastructure doing that. And you try to explain, well, it's embedded software, and there's reliable distributed systems. They run the stock market. It doesn't work. We came away from that meeting deciding, okay, we have to build it and show them. And in fact, this March, we're going to have a demonstration of a base station, which basically consists of 1U rack mount servers connected by gigabit Ethernet. And we'll have the service providers come in and say, go ahead, turn off any machine here, and you won't drop any cell phone calls. And there's a lot to be done in terms of failure detection, rapid failover, and monitoring for that system. The whole system also has to track Moore's Law, because there's always upgrades to the system. And what you'd rather do is slide either more processors in the rack or replace the existing ones with faster processors and still be able to run the same software. So our system actually supports a heterogeneous mix of processors. So the RDL interpreter and configuration system that runs on the infrastructure takes the RDL it queries all the stuff in its networks, finds out, oh, I got 2 alphas and a P4, 2 gigahertz, et cetera, and it decides what modules to run where. And as you change processors, it dynamically decides that. So this is the very high-level architecture of our infrastructure system. We've made the decision to interconnect all the processing units by an IP network, primarily because we want to ride the cheap commodity equipment. We want to use the 1U rack mount servers that are going into ISPs. We want to use the gigabit Ethernet networking that's becoming really cheap. This is actually a tremendous advantage for us over traditional equipment suppliers because they're building basically dedicated hardware, which granted they build in the volumes of hundreds of thousands for base stations, but these things are built in the volumes of tens of millions.
How much does a typical base station cost? How big is a hardware?
Okay, so a Qualcomm CDMA base station is about 5 full-height racks of equipment. And costs of base stations are, it's very hard to get accurate numbers, nobody tells you, but they're in the $100,000 to $200,000 range. GSM base stations are cheaper because they've had more competition, open standards, and you can get some of those now for the $50,000 to $60,000 range. But compared to the prices of a few rack mount servers and gigabit switch, it's not bad. And in fact, we have a really nice data point between last year and this year when we designed the first system. The gigabit prices per port came down from $500 a port to $150 a port this year. And the servers we were looking at came down from about $5,000 to $3,000. So we can provide cheaper equipment every year to our customers without having to redesign anything ourselves. Now, one key thing, there's two key components to the architecture. Up top, there are 2 slightly specialized machines in the cluster. Something has to do the A to D and D to A conversion to get the data into and out of the network. It'd be too expensive to put that capability on all the machines, and you don't need it. There's only a few points where that happens. So there are some machines, they're still the same server machines, but with an A to D or D to A card in it that serves that particular function. And the other thing is, this was a simplifying assumption, our control machine. We decided that in building a reliable distributed system, it's a heck of a lot easier if you have one place to stand. So there's one machine in the system that is assumed to be reliable. So you can spend however much money you want to get the reliability you want on that machine. You can buy a tandem machine or whatever. What it does is it just does the control and configuration of the system and holds the state. It turns out that the state in the base station is pretty small. So there's a few channels, tens of channels, each assigned to particular users going to particular places. That's really about it. And so this control machine holds all the information on what machines are doing what processing. If one of the machines goes down, it assigns another machine to do that. As long as we assume that machine is reliable, we don't have the problem of maintaining distributed, reliable control state, which would greatly complicate our system. It also gives our customers the option of, we say, OK, you want 5 nines? That machine there is $30,000 from tandems. What if you want 3 nines? You could buy a $5,000 machine. And then we'll see how important 5 nines really is to them. And the other thing, as I mentioned, was the automatic layout. So we have a processing graph described by RDL, which on a single processor just gets instantiated in one graph. Now, I should say the automatic part of the automatic layout is not fully working at this point. It's partially automated. But the goal is I can have whatever sea of processors I want there, and I can take that single graph and lay it out and multiply it, because one of those graphs is for a single channel, and a base station might have tens of channels, and it'll lay it out using the resources I have. A really important aspect about our system and why we can achieve 5 nines in a cost-effective manner is that all the red machines there are those signal processing machines. They're the same basic hardware. So rather than, normally when you build a 5 9 systems, you have 2 options. You can build each individual piece of hardware to be extremely reliable, or you can have redundancy. You can have a backup for every piece of hardware you have and have some mechanism to fail it over. Well, all those machines are the same. So we can have one machine that could back up any of them. And now that becomes a lot cheaper. You can do a simple calculation which gives you probability of failure of any machine and tells you how many hot backups you need to maintain in order to really reach your desired level of reliability. A key thing is that these hot backups, they have software sitting there instantiated for many, many different processing chains. So they're ready to go. They're all configured. And then when the failover happens, we just tell it, well, this machine failed. You need to run that processing chain. Here's your input. Here's your output. And it just starts sucking data across the network and taking over the processing from that element. So the fact that we have this generic processor backbone actually makes reliability much, much cheaper. Yeah?
Can a single machine handle a channel? And if so, what do you get by pipelining channel across multiple machines?
Okay. So when you digitize the spectrum, you get one big chunk of data in. And actually, the first step is to take that chunk and separate out the multiple channels. So that's a common step between multiple pipelines. So actually, the right pipeline would sort of look like, for a cellular system, the reverse. Okay, where you have one common step, and then it splits out into many. Once you split it out, you can do many channels on a single processor. So you'd actually want to have multiple chains instantiated on each one. So for example, in AMPS, you can do 10, and GSM, I think there's some performance numbers. You can do about 8 on a single processor. So there are some naturally common steps in there. And then after you get over those common steps, this falls into the class of like embarrassingly parallel applications. So yeah, speaking of performance. So we're actually, now that we have a sort of core set of useful waveforms, 802.11, TDMA, GSM, AMPS, we're starting to do some benchmarking on different processors for different applications. And this is a work in progress, but I thought I'd show you some of the partial results. We've looked at the 200 megahertz strong arm, which is a nice processor for handheld. It's in the iPac and some of the Jornadas today. PowerPC running at 533, a 600 megahertz Pentium, and the latest, or no longer latest, gigahertz Pentium. And I've chosen just 3 examples here to show you. CCK decoding is the despreading and demodulation step in 802.11. This is one of the areas, by the way, where we've made a tremendous algorithmic improvement in the last 3 months. We got 2 orders of magnitude speed up in the decoding process, which is critical, because that's an 11 megabit per second system. And without that algorithmic improvement, there was no way we were looking at running it in real time for the next 3 years. Now, on a strong arm 200, we're a long way away from doing the 11 megabit 802.11 system. But as you see on the PowerPC 533, it's 60%, and on the Pentium 3, it's 70. The next one is, this is just recent work we recently completed. This is the GSM base station.
What does the percentage mean again?
That's percent of the CPU that it's taking to perform that function. So it tells you that, in that case, we can't quite run 2 of them on a PPC. The second row is a GSM base station. This is a 1 sector. Base stations are set up in sectors where you can, if they're actually divided into 3 sectors spatially so that you can support 3 times as many users. And each sector has 1 200 kilohertz channel which supports 8 users. Now, we can now do 1 GSM, basically what is considered a base station, in 200% of a 1 gigahertz Pentium, which was pretty encouraging because there are 2 gigahertz Pentiums now, and we can claim to be able to do a GSM BT base station on a chip. That's bring in the whole wideband, select out your channels, process all the voice channels that are in that sector. And on the TDMA side, that's the mobile side, we've implemented that, and it only takes 85% of a 200 megahertz strong arm, which is great, because that means we can run analog and TDMA and maybe, if we're lucky, GSM on a mobile that just has a 200 megahertz strong arm in it, which, depending on what you run the speed at, has power dissipation between about 40 milliwatts and 450 milliwatts. So that points the way to the future of mobile devices. So one comment on processors before we get on to the next slide. So, when we started, all these things were done in DSP processors. And you might wonder, why are we using these things that are more general purpose RISC-like, aside from the obvious software engineering advantages? Well, something happened along the way, and that something was called multimedia. So when multimedia became a big thing, everybody started adding instructions and features to their processors to better support multimedia. Well, it turns out multimedia is it's really signal processing. It's processing audio and video signals. So they started adding things to general purpose processors that before you only found in DSPs. For example, the single cycle multiply accumulate, which is like, a core element of any DSP, is now in the PowerPC. They have vector instruction sets like MMX and AltiVec on the MMX on the Pentium and AltiVec on the PowerPC, which are great for signal processing and have been in many DSPs for years. So what you're starting to see is a slight convergence of the architectures. On the DSP side, they're realizing, gee, we got to do network stacks and maybe have a couple processes running, and they're starting to support something that looks more like a real operating system. In fact, some of the latest analog devices DSP actually has something that DSPs have never had before, which is a memory management unit. It's not fully fledged. You can't actually run virtual memory, but hey, it's a pretty good start. So what you're seeing is sort of a convergence of the architectures. And I think what you'll see in the future is that all processors will have to be capable of doing some kind of signal processing. Whether you're talking about voice or video or speech recognition on the general purpose side or traditional DSP functions, they're all going to have to do some of that. And it's how well they support the other functions. What we're betting on is that the people that win that race are the general purpose people. Why? Because they have more volume and more money to throw into R&D than any particular DSP company does. And if you notice, if you track clock speeds of DSPs versus clock speeds of general purpose processors, the DSPs are not tracking Moore's law because they don't have the money and the volume to justify all the R&D that Intel and Motorola do to bring out the next generations. And the general purpose world has suddenly woken up and realized that embedded low power applications are important, and things like the StrongArm and Xscale are looking like really good targets for this kind of work. So when I talked to Susan before the talk, she told me about the efforts in looking at domain-specific processors, and would software radio be an interesting target? And my gut feeling was, yeah, I think so. So I walked around and talked to everybody and said, well, if you could add 3 instructions to the Intel processor, what would they be and why? And this is just a smattering of some of the ideas, but some are very basic and some are kind of interesting that are specific to software radio. So the first one is, the first guy I talked to complained about caching strategies. He said, here's the problem. He said, usually you use, like an FFT, as I mentioned, or many algorithms, it turns out that the data bits you want, A, they're separated far apart, and B, they're often like in a 2K multiple apart. So if K happens to be right, they're going to map to exactly the same cache lines that the other piece does, and you actually just thrash your cache all the time. And he said, you know what I want? He said, I don't want cache addresses by least significant bits or however it's done. He said, I just want a hash table that I want to hash my cache addresses. Because my data patterns are very variable, and there's things I use a lot, and they're multiples of 2K, and I don't want to have to worry about some particular weird caching strategy bashing my data. So one interesting idea. Second one is really quick and precise clocks. Like I said, we got to support real time, starting with semantics at the high level language, but they've got to map to something down in the processor. Now there are clocks like cycle counters on the Pentium. The problem with the Pentium one is while there's a cycle-accurate clock, it takes forever to read the clock, okay? Which kills you and you don't know the accuracy. The PowerPC is a lot better. But we really need clocks that you can accurately grab and attach to events or data or functions as you need. Here's an annoying thing, faster MAC instructions. It turns out that the PowerPC does floating point max faster than it does integer max. And in fact, I don't know if it's true in the latest version, but on the previous one, I looked in the manual and I added up the cycles to do an integer MAC, and it was exactly the same number of cycles it took to do an integer to floating point cast, a floating point MAC, and a floating point to integer cast. So integer MACs are really important, and it kind of annoys me that on one hand, I'm really glad to have fast floating point MACs. That's important for a lot of things. But for a lot of other things, you don't naturally keep your data in floating point format, and you don't want to have to cast it. Yeah.
So this is still important, even given your new algorithm?
Yeah, MACs are still
even more important.
Yes. Right, because we're using more MACs, right? Yeah. So we want to keep pushing it down, exactly. So the next one's my favorite. I didn't really understand it at first, but one of the guys said, what I want is a branch on random instruction. Okay, like what the hell? So he said, look, there's a lot of stuff in encryption where you really want random numbers generated, and this whole thing about randomly moving your mouse or keyboard is ridiculous. And there's a lot of work now being done on randomized algorithms, or in signal processing, whitening processes, where you really want a white sequence. And he said, here's how you could generate it. He said, you put a diode on the chip and a 1-bit A to D converter, and you sample the thermal noise on the diode. That should be a pretty good source of randomness. And they said, well, yeah, but why do you want to branch on random? He said, well, I can easily generate a random bit from a random branch, but for randomized algorithms, I actually want random branches, and it would be much more expensive to put in a conditional, get my random bit, and generate a random branch. So that was a pretty interesting kind of instruction. And the last one is directly related to some signal processing applications, in particular spread spectrum, spreading and despreading. You would not believe how much computation, we didn't measure it, but it would reduce an incredible amount of computation. It is a one-cycle conditional sign flip instruction. When you're dealing with spread spectrum stuff, all your data is actually ones or minus ones. And if you send a 1 bit, you send the data, and if you send a 0 bit, you send the negative of that data. And when you receive, you're constantly flipping and reflipping these things. It's a very simple instruction that would actually save a lot of processing. And I think if we thought about it, there's a lot more of those kinds of instructions that would be specific to certain signal processing applications. So I think, so before we close, I thought I'd tell you one slide about our business. We were founded in September '98, and as Susan mentioned, we were a spin-off from the MIT Spectrumware project, which was the topic of my PhD. Did some software radio research. So we've been building software radios for 6 years, going back through that work, and we're 21 people today. We have expertise in 2 areas. Now, I've talked about a lot of different areas, but we're really good at building the systems. That's not only physically putting the A to D converters and memories down, but modifying the operating systems, building the middleware, dealing with the timing, and building the software for the waveforms, including the different algorithms. So the way, Susan mentioned we're profitable, which is a kind of unique thing these days. And, and in fact, just so you know that there's another way to start a company. We're 3 years old, we're 21 people, and we did this all on a total of $300,000 in capital invested in the company. And one of the reasons we're able to do this is when we go talk to potential customers and tell them about, hey, here's the software radio, here's all the cool things it can do for you, we got the software. They're like, okay, cool, but that software won't run in our system, and we don't actually know how to build a system that would run your software. So we say, fine, hire us as consultants, which they do at a nice rate, and we design a system that fits into whatever their wireless system is. We design an architecture, build them a prototype. They pay us to do that. Once they build it into their product, it becomes a platform for us to license our software on top of. So we're actually able to bootstrap the business that way and help our customers get products to market faster. So last slide is my shameless recruiting plug. I think you can see that we're looking for people in a lot of different areas. We're looking for people at both the master's level and PhD level. Out of 21 people, I guess we have 5 PhDs, although I don't really count anymore. So maybe it's 4. But in different areas. And as I mentioned, the real challenge in these areas is where these areas intersect. So getting a computer algorithms guy to sit in the same cube with a DSP guy, and for the first month, it's kind of interesting to try to listen to their conversations. They just can't talk at all. They have completely different languages. But eventually, they get to it, and then they start coming up with really creative solutions. So if you're in any of these areas or any of the things I've mentioned, we'd love to talk to you. If you can't talk to people outside of your area, don't bother applying, because that's absolutely a prerequisite for what we do. And that's where the most interesting stuff is.